Thank you, Bob. Thank you, Washington, for that introductory talk. And good afternoon, everyone. It's nice to be with you this afternoon. Hope you also have a sunny afternoon, as we do here in Nottingham. So, I'm Paul Blunt. I've spent most of my career as a GNSS receiver designer, and now that forms most of the topics of my research here at Nottingham. So, I'd like to talk to you today about the GNSS receiver itself, the GNSS sensor, one of these core sensors to our navigation, and give you a little insight into hopefully what the effects of interference are on the GNSS receiver, and also what this thing called spoofing is, and what the effects of spoofing are, what we can do about it in the receiver, and how we could mitigate it, but also what the limitations of this sensor are. So the topics I'd like to cover, it's quite a deep topic. GNSS interference and spoofing requires you to sort of know at least something about the GNSS receiver, what goes on inside the box. So I'm hoping today just to give you a little insight into what is within the box, what GNSS signals are actually to start with, so that we can get a better appreciation of why interference and jamming and such things are a problem with the GNSS receiver. And also, if we look at the different elements of the GNSS receiver, we can hopefully get an idea about what we can do within the receiver to mitigate these things and what the limitations are. So we're going to start off with Gnss Signals, talking quickly about those, just give you some important information about those. Then we'll look at the receiver. We're going to look at different types of interference and things and what the effects might be. And then we'll look finally at spoofing, GNSS spoofing. Okay, so start off with Gnss Signals. Here's a kind of a slightly simplified diagram, but it works for what we need. So the GNSS signal itself here is made up of a carrier wave, so it's transmitted on a carrier, and there are various different GNSS signals, but they're living between sort of 1.1 and 1.5 gigahertz. So you have to imagine this carrier's switching, oscillating very fast, this sinusoidal carrier, and that carrier is going to be multiplied by what we call a code sequence or a pseudo-random noise sequence, this PRN sequence. And this is effectively like a random set of bits that are flipping between plus and minus 1, and they may be 1,000 or 10,000 bits long for some of these signals. But essentially just random bits that are being transmitted. And how you make up the signal is you multiply this carrier wave that we have at the top by this code sequence, and what we're ended up with is a modulated signal that we see at the bottom, which is the same carrier wave, but you have these where the code transitions as such, you have these changes in phase to the modulated, to the carrier. So we're changing the phase of the carrier with the code, and the reason for doing this will hopefully become clear as we go through. But important thing to realize is that every GNSS satellite that's above us is transmitting its own unique code, and that's how we tell the difference, how we tell one satellite from another. Okay, so the effect of that code, we can see here, what we looked at just above was what it looks like in the time domain. So left to right, we've got time going across. But here we see what the signals look like in terms of frequency. So on the x-axis, along the bottom here, we've got the frequency of the signal. And we can see if we were just to take a tone, like on the left, just a sinusoidal carrier, what that does is just create a spike in the frequency domain at that frequency, whatever that frequency is. In our case of GPS, maybe 1.5 gigahertz. But this code, once we've applied this code and we have these phase changes, the reason that code is also called a spreading code is what it does is it takes the power of that carrier wave and spreads it across quite a wide bandwidth. So here we can see it being spread across so you can see the peak level is reduced, and you can see that it creates this shape. It's called a sink shape, where the kind of main lobe, most of the energy is in this first hump in the middle, and that's defined by the rate, the switching rate of that code. So the faster that code, the wider the bandwidth the signal will be spread across. So that's why we call it a spreading code, because the faster that switching is going. Another thing to point out is here I've shown in time domain the carrier in only a few cycles for every bit of that code. In reality, that carrier is 1.5 gigahertz, and the code rates we're talking are a few megahertz. So generally, you'd have, like in the case of the normal GPS signal that we're used to picking up, we'd have 1,540 cycles of the code for every one of these bit transitions, or the code transitions. But this way, we can see it a lot easier. Okay, so that's what the signal looks like, and we can see there the effect of the spreading code. Now, one thing you'll hear quite often from people is that the GNSS signal, if you were to just go out and look at it and get an antenna, go outside and try and look at this signal, they say you wouldn't see anything. You just see noise. It's buried in the noise. The signal is so weak, it's buried in the noise, and that's an important factor to consider when we talk about GNSS signals. So, and hopefully we can prove that here to you if we look at the actual and the power level that's received at a GNSS antenna. So, for example, here for the GPS signal that most of us use, its received power level is minus 158 dB watts. Don't worry if that doesn't mean anything to you. I'll try and make that clear in the next slide. But what you have to appreciate is that number is incredibly small, and hopefully we'll be able to show that to you. And the reason for that is the satellites are quite far away from us. They have a reasonable transmit power, but they are 20,000 kilometers from us. So when we pick up a signal low to the horizon, it might have passed through nearly 25,000 kilometers to get to us. And we can see here on this, just to give you an equation, that for the path loss, you can see it's related to r. Here is our distance, so the path loss squared it's proportional to the path loss squared. And also, we can say it's the loss is also proportional to the frequency of the signal. So the higher frequency of the signal, the more loss we're going to have in the path. So in the case of GPS, here we have 184 dBs of loss going from the transmitter to the receiver. So what does that mean? If you say, hang on, Paul, I haven't got a clue what minus 158 dBs actually means. Here's a little table because we don't all deal with decibels every single day. So 1 watt, if we effectively take 1 watt, we write that as 0 dB watts. And if we take a factor of 10, if we multiply that by 10 for 10 watts, we'd say that's 10 dB watts. It goes up by 10 decibels. But that's where the similarity changes. So if for every order of magnitude in the watt scale, we just drop down a value of 10 in the dB watts. So one way to say it is if you go from 1 watt down to a milliwatt, you're divided by 1,000 times, but actually in dB scale, that's only minus 30. If you divide by 1,000,000 times, that's minus 60. So a microwatt is minus 60 dB watts. The GPS signal, on the other hand, if you wanted to write it in watts, instead of 6 zeros in this watt scale, we'd have 16 zeros before any significant figures here. It'd be 10 to the minus 16, which means that we end up with and that's why we talk in decibels, is because this power level is so unbelievably small. So even if you think about a microwatt, that's still nearly 100 decibels stronger than the GPS signal. Okay, and just to throw some more decibel numbers for you, if we just think about how strong that is at the receiver, if we just think about thermal noise, so just noise. If our antenna in our receiver is just a piece of metal, and we have free electrons moving around in there, and as we're not at absolute zero, there's some noise on that conductor. And the amount of noise on that conductor is this value here of minus 204 dB watts for every hertz of bandwidth. And for our standard GPS signal, we've got about 2 megahertz of bandwidth. So if we work out the amount of noise power in that 2 megahertz of bandwidth, we come up with this number of minus 141, say, as a rough calculation. And we can see that that's 17.5 dB stronger than our received power level. So if we look at a signal across the spread bandwidth of the signal, we don't see anything when we look at just the output of an antenna generally, because the signal is way below that level, and that's what we're trying to point out here. So to visually look at that, you might think about our shape here of our spread signal, but actually what we're seeing is this noise that's sitting sort of 15 or 17 dBs above the received power level. And the reason that's important is because the signal is so weak, then that means that it's quite easy then to interfere with. So if we look here at the so before we get onto interference, we'll just talk about what goes on in terms of the receiver. So what GPS could be called what we call a spread spectrum signal. So here on the left, we've got what we talked about so far, starting off with a signal of relatively narrow bandwidth, multiplying it by a code and spreading it over a wide bandwidth. Then we pass it through a channel in the middle, and that adds noise and potentially interference to our signal, which is generally at a much higher level than the signal, perhaps. But then in the receiver, what we're going to do is we're actually going to multiply that code on again, and we're going to de-spread the signal. We're going to reduce the bandwidth right down, and that's what this is trying to depict, is the signal going, after it's gone through the channel, the blue signal is then reducing back down in bandwidth, and we're able to pull that out of the noise while suppressing the noise down to a reasonable level. And that's what goes on inside the GNSS receiver. That's how we're able to recover the signal while suppressing the noise. So this process of multiplying by the code in spread spectrum signals is actually used to reduce interference. It helps you spread out interference over a wide bandwidth and gives you a certain resilience to interference. But generally, a spread spectrum signal is transmitted at a much higher power level when you talk about communication systems and that sort of thing, as GPS is rather unique that it's incredibly weak. Okay, so now let's have a little look at the GNSS receiver itself, what elements make up a receiver, and then we can start to see about how this interference affects us. So here's sort of a block diagram of the receiver. We've got our GNSS signals coming in on the left, and I've split the receiver into kind of 4 parts because those are the parts that we can do things in the receiver to try to mitigate interference and spoofing and so on. So we've got the antenna, which just is the part that converts the radio wave into an actual electrical signal we can feed into our receiver. We have a front end that down converts the signal from 1.5 gigahertz down to a reasonable low frequency that we can deal with. And then we have a large amount of signal processing in the receiver. This is digital at this point in the yellow, where the receiver is tracking every one of the GNSS satellites in the sky, each with individual tracking loops and different signal processing for every satellite. And then finally, in the blue, we've got the actual navigation processor. That's taking the measurements out of all these tracking channels and using all the measurements of all the range to the satellites in order to work out where we are on the Earth's surface or above the Earth's surface, wherever we want to operate our GNSS receiver. Okay, and then in terms of interference, when we have a number of different types of interference, we've got quite a lot of cases of unintentional interference which can affect a GPS receiver. So because the signal levels are so small, our RF sections, so those antenna and front end sections, are very sensitive to noise just in the integration of our GNSS chips into the system around it. So there could be a number of noise sources that a GNSS receiver has to deal with that are just entirely either self-generated or generated from sources nearby, entirely unintentional, just communications devices, any interference from other sources like Wi-Fi, Bluetooth, whatever you've got transmitting around you. Then we also have types of interference that are intentional, sort of malicious, which we might call jamming. So somebody actually trying to stop our GNSS receiver from working. And both of these we can deal with to a certain extent in the receiver. The harder one is generally the intentional one, because people have actually thought about how to cause us the worst effect inside the GNSS receiver. So, but what I want to point out here is that even within interference, you have many different types. We can have here what the red signal. So what this is meant to be is the blue is meant to be the bandwidth of the system that we're dealing with. And the red is meant to be a narrow band jammer. So this could just be a sine wave, could just be, as we saw, just somebody relatively easy to knock up in your garage or something, or you can buy off the internet, just a sine wave jammer that you can produce at 1.5 gigahertz or something like that. A more sophisticated jammer would be one that sort of does a similar thing to creating the GNSS signal, that spreads the interference over a wider bandwidth, and that's harder for us to deal with in the receiver. And then we have some other types, like the green one here is meant to depict something that's sweeping across the bandwidth. So there's a common jammer that's quite effective against GNSS receivers, is one that constantly changes its frequency across the bandwidth, so that you can't just easily filter it out and things like that. And then we also have pulsed interference, so interference that turns off and on. This is often unintentional as well. Landing systems for aircraft tend to be pulsed, and those can interfere with the GNSS signals. So we've got to come up with ways in the receiver to deal with all these different types of interference. Okay, so this is what I'm showing here, is just a typical performance of a GNSS receiver without any protection. So along the bottom, we've got how strong the jammer is relative to that noise level in the ear that we talked about in the receiver. And on the right hand, on the y-axis, on the vertical axis, we've got the kind of the estimated signal by the receiver, so it's its own signal to noise ratio effectively. So when in this case, when there's very little interference, that was close to 40, and a GNSS receiver will tend to lose lock or be useless, at sort of 20 or less on this scale. So, and these different lines are different types of jammers. So we've got a kind of single frequency jammer in blue, some multiple jammers in red, and then this sweeping type of jammer in green. And you can see the sweeping jammer affects the receiver at a lower signal to noise level, so it has more of an effect on the GNSS receiver. But effectively, what we're showing here is when we get a jammer to signal ratio, in this case of around 40 dBs, we can't operate the receiver anymore. It would just fail. And that corresponds to something in the region of about 10 to 100 milliwatts of jamming power at about 1 kilometer away or something. And that's something that's very easy to make, that kind of jammer. So without any protection, quite easy to interfere with a GNSS receiver. So what can we do about it? Well, we can do things in every one of those blocks within the front end. We have one of the most effective ways of dealing with interference is to use multiple antenna inputs to the receiver, and that's depicted on the left-hand side here. So here you can control the inputs or the outputs of each one of those antennas, and the idea, what this is trying to depict, is that we could adjust the response pattern, the gain pattern of the antennas that we receive, so that we can point effectively towards the signals that we want, these kind of blue signals in the sky. But if we've got interference probably coming in at a low level because it's near the horizon or something, we can create a kind of dip in our antenna and remove that interference. So that's a very effective way of dealing with both interference and spoofing, for that matter, when we get to that. Then in the front end, we have options for filtering, which is useful, particularly with unintentional interference, because those tend to be fixed frequencies. And we can monitor the power level of the receiver. So if we suddenly get big jumps in the input power, we know that we've probably got somebody trying to jam us. And then most receivers nowadays, even mass market receivers, will have some sort of filtering integrated into them in the signal processing that will allow them to filter out at least the simple versions of these interferences, the tones, maybe even the sweeping jammers. And that gets into adaptive filtering. So these are signal processing techniques. And then on the navigation side, we can also help the effect of these on the receiver by looking at the consistency of our navigation solution, by doing more filtering, or potentially integrating with other sensors as well that allow us to kind of work throughout these periods where we might see GNSS interference. So there's a wide variety of techniques, and some of them work for some of the interference. Adaptive filtering works very well for narrowband interference, but wideband interference, you really need the multiple antennas and so on. There's different things. There's no one magic bullet here that kind of solves all of the interference problems. But just to give you an indication of what we can do in the receiver, here's the case of those same kind of jammers with adaptive filtering, and you can see now we've been able to do kind of 30 dBs better. So we've now got a jammer to noise ratio of 70 dBs before our receiver sort of starts to fail and have problems, and that's about the best we can do nowadays with those kind of adaptive filters. And that means that we have greater level of protection, so we need more like maybe 1 watt to 10 watts of power at 1 kilometer of jammer power to take out the receiver, rather than the milliwatts we were thinking of before. So we've certainly been able to make things better in recent years with these kind of techniques. And you can combine these techniques some of these techniques to provide even better protection as well. Okay. So hopefully that gives you some indication about what we're doing in terms of GNSS spoofing. I'll now just, interference. I'll now just talk a little bit about spoofing. So what spoofing is effectively, instead of interfering with the signal, we're trying to fool the GNSS receiver by giving it a fake signal, one that's not either a faked or a copy of the signal that in some way gives us an error in our position solution. And the way we go about doing that is we can go through 2 optional stages to start off with. We can sort of use a receiver to pick up the signals that we're receiving in the sky, so we know what frequencies and what delays all of those signals are being transmitted on. And we can also maybe gather information about the target that we want to spoof. If we know its rough location, that can be helpful to us. Then most spoofing attacks start with can start with the middle stage is to actually jam the receiver in the first place, and that can cause it to lose lock and forget which satellites it was tracking and on what frequencies it was tracking, which makes it easier to spoof afterwards. And then the actual spoofing attack itself comes later, and that can take a number of forms, as we'll see here. So here's kind of 3 basic ways of spoofing a signal. You can take the signal you're receiving on the left-hand side from a satellite and just replay it to the antenna. You can actually, you can forget about the signal that you're actually receiving and just generate GNSS signals yourself and try to fool the receiver that way. And that's kind of the intermediate level of spoofing. And then we now have people thinking about very sophisticated ways of spoofing where you're receiving the signals that are there, and then you're sending out a signal that first kind of matches those signals perfectly, and then drags the receiver away to a new location which is false, or even more, this technology that's now called nulling, where they can also try to remove the true signal from the receiver as well. So lots of different levels of spoofing being taught. Most of what we've seen is in the first two categories, I'd say, to date, but it's becoming easier and easier to do this more sophisticated version of spoofing. Okay, so I'm gonna have to hurry up a bit, but just to see what the effect of spoofing is, I just wanted to show you that what the receiver's doing, as we talked about, is trying to line up these codes in the receiver. So if you imagine, it's lining up a code for each individual satellite, and when it does that, it gets what's called a correlation peak. And here you can see like a large spike. So when the codes are misaligned, is anywhere but 0 on that graph, and then when they're lined up, you get a big spike. And if we zoom in, it looks a bit like a triangle there. And that's what the receiver tracks. It sets up a couple of points around it to track the received signal. And when we talk about sophisticated spoofing, what we're doing is actually, here you see the kind of correlation peak of the true signal in blue, and then a perfectly matched in delay spoofing signal that's but lower power than it. And then a very clever spoofer slowly increases the power so that the receiver starts tracking its signal instead of that true signal, and then it can pull it off and start changing the delay and the location of the receiver. So that's very much more difficult to detect and notice than when you've just been jammed or you've got a high power spoofer coming in right from the start. So similar to interference mitigation techniques, we have a range of ways of dealing with spoofing inside the receiver. The best one probably, is again the multiple antennas looking at the angle of arrival of the spoofer and trying to mitigate it by creating nulls in the antenna pattern or dips in the antenna pattern. But we also have ways of detecting spoofing using either the received power level in the front end, or looking at that correlation shape itself and seeing if it's distorted or if there are multiple correlations within our receiver, because we might have the true signal still there and the spoofed signal in the same data, so that we can actually, in some cases where they're both present, discard the actual spoof signal and keep tracking the true signal. One thing that's going to help us detect spoofing in the coming years is something called navigation message authentication, and that's where the GNSS satellites are now going to transmit encrypted data to us, which cannot be easily known ahead of time. So it's very hard for that intermediate level of spoofer where they don't know what the navigation data is of the satellites to actually spoof the receiver, and that gives a good level of protection for quite a number of the cases, but not all of them. There's always holes in this, and it needs similar to to interference, we need a range of different approaches in order to really detect and mitigate these things. So we have that coming in. Galileo is just starting to trial its navigation message authentication, so hopefully that'll come in the next few years, and we'll be able to improve the performance of the receiver. But we can also do things within the navigation processor Filtering, again, consistency checks within the receiver to say whether our ranges or our measurements are out of certain bands. And we can also use inertial units and things like that are very, very good at spotting spoofing, because you can bound the kind of errors and the movement of your platform if they're available. Okay, so just a few words to sort of sum up about these things. That firstly, about interference, we're now pretty good at detecting when we're being interfered with. That's quite reliable, but we don't have a single solution to mitigate all types of interference. So we can make a vast improvement on an unprotected GNSS receiver, but there's always going to be a jamming power that will overwhelm our receiver that you cannot. And because the signals are so weak, even though we've got these sophisticated techniques in the receiver, that jamming power is still quite low. It's still something that you can produce with a relatively basic set of kit. So we still have a vulnerability there, even with all of the techniques combined that we can use in the receiver. And for spoofing, it's a similar story as far as I'm concerned. The detection techniques are improving, and the navigation message authentication will help that. We've got definitely some research in the coming online, which will improve those detection techniques, make them more reliable. But again, there's no single solution that covers all of the different types of spoofing that we can encounter. I've just shown you a very top level sort of different types of the spoofing, but there are many different categories, and some mitigations are good for some categories, some for others, but nothing that covers every possible defense. And in fact, there are some cases of spoofers which we are by definition impossible to deal with. Those where the spoofer is just very much stronger than our received signal, much like the jammer. There are limits to what we can do in the receiver, and also if the spoofer is clever enough to effectively cancel out or null the true signal from the data that we're receiving, there's nothing we can do there as well. So hopefully that gives you some indication about what we can do in a GNSS receiver, what areas we can improve, but ultimately the fact that we are going to need more than just the GNSS receiver for a truly reliable solution.